Started to record stuff. Okay then. Uh, so yesterday we have started the course regarding the sequence and series. So yesterday I have taught the definition of a sequence. So I'm going to recap the definitions and theorems that I have taught yesterday. So basically, sequence is a map from natural numbers n to real numbers r. So few examples are minus 1 power n, sine n pi by 2, 1 by 1 plus 2 power minus n. So these are some examples of sequences that we have seen in our previous class. Okay. So after I have defined what a sequence is, and then I have given a definition on how to check the convergence of a sequence. So a sequence is said to converge if for every epsilon greater than 0 there exists an n naught in n such that mod of xn minus xn naught is less than epsilon for all n greater than or equals to n naught. Sorry, this is not n naught, this is the limit. So this is an equivalent definition for limit xn, n approaches to infinity is x, and which I'll also be denoting it as xn approaches to x. So I have given the definition of convergence, and I have given some examples for convergences, and we have proved some theorems. Let me recollect few of them, few of the important theorems that we have proved in the previous class. Am I audible? Varshit or Diksha? Strange. Recording. Okay. So today we'll start with some examples. So now we have a sequence p power 1 by n. So I claim that limit n tends to infinity p power 1 by m equals 1. So what this basically says is that, say I have 2, and if I take 2 power 1 by m, as n tends to infinity, this goes to 1. So in our JE days, everything we used to intuitionally write this, but now we are going to mathematically establish this particular limit. So let So now I let xn equals p power 1 by n minus 1. This implies that p is equals to 1 plus x whole power n, which implies p is equals to 1 plus, now we use our binomial expansion, nc1x plus nc2x square plus so on so on. Okay, so this would imply that if p is 1 plus n times x plus n into n minus 1 so on to infinity, this particular entity is a positive number. So this is something plus positive number is p, implies that p should be greater than or equals to 1 plus nxn, implies xn has to be less than or equals to p minus 1 by n. So now we have a sequence 0 less than or equal. Okay. 0 less than or equals to xn less than or equals to p minus 1 by n. So yesterday we have showed that some constant times n goes to 0, and this is 0 as n tends to infinity. Hence, by Sandwich theorem, this goes to 0. Implies p power 1 by n minus 1, which we defined what xn is to be. This also goes to 0. Implies p by 1 by n minus goes to 1. So this is how we proved one small theorem. Okay. Now I'll go to the next theorem. Somehow your friends like all my comments. The class is going to start at 10, but nobody turns up. Interesting. Okay. Okay, so now I define a sequence yn equals n power 1 by n minus 1. So now, so basically I'm trying to prove that limit n tends to infinity, n power 1 by n goes to 1. So infinity power 1 by infinity is 1. How? So let me prove. So let there be a sequence yn greater than or equals to 0 for all n in n, such that yn is equals to n power 1 by n minus 1, implies 1 plus yn whole power n equals n, implies n is equals to 1 plus nc1 times yn plus nc2 times yn plus so on implies n is equals to 1 plus n times yn plus n into n minus 1 by 2 times yn square plus some positive number a. So this implies n is equals to 1 plus n by n plus n into n minus 1 by 2 times of yn square plus some positive number implies n is greater than or equals to 1 plus n into n minus 1 by 2 yn square, because this is positive, this is positive, this is positive, so obviously n has to be greater than this value, implies n minus 1 divided by n into n minus 1 by 2 is greater than or equals to yn square, implies under root 2 by n is less than or equals to yn. So now we have chosen yn to be such that 0 is less than or equals to yn less than or equals to root 2 by n. So now n goes to infinity, this goes to 0, this goes to 0. By sandwich theorem, this goes to 0. Okay, so yesterday we have proved the sandwich theorem, and using those theorems we have proved that two such sequences goes to 0. So the limits that we have learned in our JEE days, they are intuitively written, but this is how hard math is behind those convergences. So now we move on to the next concept, monotonic sequences. So now a sequence, again recollect the definition. Sequence is a map from natural number to R, so denoted by xn or xn this way, is said to be monotonic. So after monotonic you either have, it is either monotonically decreasing. So a sequence is monotonically decreasing if x1 is greater than or equals to x2 is greater than or equals to x3, so on. So every next term of the sequence is lesser than the previous term. So for an example, I'll give you 1 by 2 power n. So we have 1 by 2 x1 is greater than or equals to 1 by 4 is less than or equals to 1 by 8, so on. So this is a monotonically decreasing sequence. Similarly, we have something called monotonically increasing sequence. So a sequence is said to be monotonically increasing if x1 is less than or equals to x2, so on to x infinity. Okay, so now why do we need these sequences? So if say a sequence basically has this monotonic property, concluding about some of its convergences is easy. So basically monotonic sequences have a good convergence property. So now I prove a theorem. A monotonic sequence is convergent under this condition. A monotonically decreasing sequence which is bounded below is convergent, and similarly a monotonically increasing sequence which is bounded above is convergent. So previously we have seen some sequences we had to expand them binomially, and then what we saw, it took some effort to prove the convergence. So in mathematics, so basically we have a definition of things. We have a definition for convergence, but the definitions are not used to prove things, because checking a sequence is convergent or not by that epsilon definition that I have given before is difficult. So we need to derive some theorems based on which we can easily tell that if a mathematical concept is actually valid or not. So now, how do I prove this? Okay. So before proving that, I'll give a definition, least upper bound. Least upper bound of a sequence. So let us say we have an xn, and if it is bounded, say we have a sequence 1 by 2 power n. So basically, if you calculate the sequence 1 by 2, 1 by 4, so on till it will go to some 0. Yeah, we proved that it's a limit. So this particular sequence has an upper bound. So all the elements of this sequence are less than 2, are less than 1, are less than 0.8, are less than 0.6, so on, so on, so on. So what is the minimum upper bound of the sequence is called a least upper bound. So every bounded sequence will have a least upper bound. Similarly, a sequence that is bounded below will also have a lower bound. So now we prove that a monotonically decreasing sequence is actually convergent. So now, if we have a sequence, we denote its least upper bound by LUB. LUB means least upper bound, LUB of xn. And similarly, we denote its greatest lower bound, GLB, by GLB xn. So what LUB xn means? It is basically minimum of all m such that m is greater than xn for all n, and this is basically maximum of all m such that m is less than xn for all n. So now I have a monotonic sequence. I have sequence and the sequence is said to be monotonic, monotonically decreasing, and I know that this sequence is bounded below. It's not bounded below, it is bounded below. Okay. So by the LUB property, there exists an epsilon greater than 0 such that there exists an element xn So there exists an x0 such that there exists an x0 belongings to the sequence xn such that this is the LUB L minus epsilon, there should be xn not here. So it means because it is also monotonically decreasing, so xn naught plus 1 comma xn naught plus 2 so on also lie in this epsilon ball, implies it is convergent. So any monotonically increasing sequence that is bounded above is convergent, any monotonically decreasing sequence that is bounded below is convergent. So now let's take an example. We have x1 is equals to 1 and we have this recursive sequence xn plus 1 equals 1 by 2 times xn plus 2 by xn. So now, firstly, I claim that all xn's belong to 1 comma 2. I mean any sequence that is satisfying this particular pattern will not exceed 2 or nor go below 2. So say this is, so we prove by binomial induction. Say it is true for 1. It is true for 1. So we assume that it is also true for n. So xn also belongs to 1 comma 2. All we need to do is prove that xn plus 1 also belongs to 1 comma 2. Binomial induction we study in our 10th standard. I hope people remember that. Okay. So xn plus 1 is equals to 1 by 2 times xn plus 2 by xn. So the maximum value that this can attain is 1. The minimum value that this can attain is 1. The minimum value of this can attain is 1. So 1 plus 1 by 2 implies minimum of xn plus 1 is 1. Similarly, 1 by 2 times maximum that xn can attain is 2 plus minimum what xn can attain is 2 by 1 implies the max of xn plus 1 is 2. So implies xn plus 1 belongs to 1 comma 2. Hence the entire sequence xn's belongs to 1 comma 2. So we have a sequence that is bounded below and above. Now we just need to check is the monotonicity. Because any monotonic sequence that is bounded is convergent. Okay. So basically showing xn plus 1 is greater than or equals to xn. It's kind of simple. So xn plus 1 is equals to one by 2 times xn plus 2 by xn, which is equals to xn plus 2 by xn minus 1 by 2 times of xn. So I'll just take f of x equals 2 by x minus 1 by 2x implies f dash of x is equals to minus 2 by x square minus half, implies f dash is always greater than 0 for x greater than 0, implies that this function is positive and it is an increasing sequence. No. This is a decreasing function which is positive, implies xn plus 1 is greater than or equals to xn. So we have a monotonic sequence that is bounded above, hence it is convergent. So what does it converge to? I'll show. So because it is convergent, let L be its limit. So L should be equals to 1 by 2 times L plus 1 by 2. L implies L by 2 equals 1 by 2L square, 1 by 2L of 1 by 4L, implies L square is equals to 2, implies L is equals to root 2. So this particular, the recursive equation that I told, it converges to root 2. That is basically Newton-Raphson approximation for root 2. Yeah. Okay. So today I'll end the lecture with the concept of limit supremum and limit infimum. So let us say we have a sequence x1, x2, x3, so on till infinity. Let alpha 1 be least upper bound of x1, x2, so on till xn, and alpha and beta 1 to be greatest lower bound of x1, so on. Let alpha 2 is equals to least upper bound of x2, x3, so on till this thing, and beta 2 be greatest lower bound of x2, so on, like that. So because we are taking least value among two sequences in which I have just removed one element, so obviously alpha 1 has to be greater than or equals to alpha 2. but beta 2 has to be greater than beta 2. So what we see is that the least upper bound of the sequences actually decrease and greatest lower bound of the sequence increase. So I define so now we have the definition for lim_sup and lim_inf. Limit supremum of a sequence xn is equals to limit n tends to infinity least upper bound of xn such that n greater than or equals to k, which is equals to limit k tends to infinity alpha k. I mean, this I am defining it to be anyway alpha k, and similarly limit infimum xn is equals to limit n tends to infinity glb of xn limit k tends to infinity beta k. Okay, so I'll be exploring more. I'll explore LUB and GLB. Of course, lim_inf and lim_sup are not such easy concepts that you can understand them just by definition. Tomorrow I'll give ample amount of definitions on what this lim_inf is and what is this lim_superior is with all the examples. So basically you need these particular concepts to basically prove the convergence of the optimal solution. Say you have a robot and you want to track some trajectories, and so you basically get some sequences, that satisfy you may not exactly get a convergence, but you kind of get some approximations by these lim_inf and lim_sup concepts. Yeah. Tomorrow I'll be giving more examples. For today we'll end this class. Yeah. Thank you all. Okay. Okay then. With that we'll end today. I'll stop presenting.